Okay, neat. Well, thanks for having me, and very interesting presentation, Dr. Dr. Roos. Yeah, very fundamental and applied, fundamental to some extent. I'm going to switch gears and go to applied side of things, and talk a little bit about big picture on what are the technologies that are out there for monitoring crop stress in the era of digital agriculture, right? So again, I'm with Washington State University. I'm associate professor here, and also direct the WSU's Ag Weather Network, where we have about 400 weather stations, and that data comes to help growers make decision making in real time to some extent. So wanting to start with precision agriculture, right? And Dr. Hayes, I'm saying Dr. Hayes, but Dr. Roos mentioned a little bit about we want to, feed the growing population and need to maximize yield and all that. And that's what precision agriculture is about, is producing more with less. And I have modified that definition a little bit to say producing more with less, but for healthy beings, right? And so with that understanding, we of course do this circle of precision agriculture where with georeferencing everything on the ground, we can do geospatial mapping with satellites or sensors on the ground, measure and analyze the variability, and then manage the crop input to some extent using what is called variable rate technology. And then towards the end of the season, we go back and again see how we did, look at yield and all those things, and keep fine-tuning this circle to some extent. And that has been the concept of precision agriculture for row field crops or tree fruit crops to some extent that we are trying to implement. And as we are talking about agriculture again, this is just a big picture overview of Washington agriculture. As you may know, we have very diverse agriculture. We grow about 300 different commodity crops in the state here. In central Washington, of course, you probably know we have a lot of fresh market apple, sweet cherries, grapevines, Maine potato, and so many crops that we grow. And most of it is agriculture, also irrigated agriculture to some extent. And so in those crops, we have several challenges that we need to address and implement these concepts of precision agriculture there. But as we speak of those concepts, right, we are seeing transition in how we grow the crops. For example, we are not growing the apples on a conventional crown-shaped trees. We are using modern architecture, modern orchard systems, we call. And there we are seeing a lot of orchards being transitioned to these new architectures, apple, cherries, and even grapes and all that. So similarly, we are also seeing transition in the way we can measure and manage these inputs to these crops. And that's where we are making a transition to what is called, from precision to digital agriculture. And it's nothing but, again, use of new and advanced technologies that can enable farmers and other stakeholders within the chain of value chain of agriculture to improve crop production. And so my talk again is going to focus a little bit up to harvest, but again, the digital agriculture encompass the post-harvest issues as well there. So what it means for us, right, when we talk about how can we monitor and manage, and this schematic here kind of provides a big picture overview, right? In terms of monitoring or measuring the variability, we have a range of tools now becoming available. We have a lot of soil sensors, localized in-field weather sensing. We used to have what is called high orbiting satellites. Now we have emergence of low orbiting satellites, so many of those, and drones, of course. And then all this data that is coming is being analyzed on the edge of the field, either we call edge compute. We can also send that data with, if there is a connectivity to cloud and to cloud compute, and then to some extent, all this coming together to manage, again, and I'm going to not talk much about management, but the management is critical for implementing precision ag concepts. And so that's now enabler in terms of, range of these technologies are enabler to implement these concepts. Again, summarizing this everything here, this concept again can be applied to any, we can call digital agriculture, smart farms, smart orchards, smart vineyard, whatever that is. The concept capabilities would stay the same. The scenarios would change. Again, we have a lot of different types of sensors available for in-field sensing, soil weather. Then we are collecting a lot of spatial data, either with drones, satellites, or the ground-based autonomous or semi-autonomous vehicles. We are also getting weather data from satellites. And then all that is again being crunched or trying to be, we are trying to crunch that on the edge. And I have some examples that I'll show a little bit later. And then that's the big picture of what is called smart or digital agriculture to some extent. So having that perspective, I would like to introduce a few things that are out there and have some use cases that are discussed, that we'll discuss to see how we are trying to use some of those sensing tools for better monitoring, and then that will enable the management side of things. Again, very applied research because I'm an ag engineer and we need to stay in the field to some extent as much as we could, right? So again, you probably know this, why we do sensing. We are looking at biotic or abiotic stress. And when we do sensing with sensors, or especially optical sensors, we are looking at the reflectance and similar attributes from the canopies and such, right? So what we need for sensing there, then of course we need sensors, the platforms, and the data analytics engine that will crunch all this data. In terms of, again, the platforms, we can be, in the field, we can be, using the fiber optic probes or taking images from the distance, like 4 optics. We can have these sensing tools on the ground vehicle, on the drones, and of course, let's not ignore the satellites, right? So we have high and low orbiting satellites capturing this data as well to some extent that we can fuse with this. In terms of sensors, there's been a lot of different types of sensors that are available now and in miniaturized format. And this slide is just putting things in one slide, but yeah. So from RGB, you can have a drone with taking the high definition videos and images there. The multispectral, anywhere between 3 to 10 bands, different types of sensors that are there. Some of the sensors now match those bands with the satellite capture, so you can compare what is captured by satellite with the multispectral imagery on the ground or with the drones. The hyperspectral domain, where we have 100+ bands, capturing the plant response, are also on the horizon. Again, these sensors a little bit tedious to put on the drones, but with manned flights or scenarios like that, or on the ground, you can capture much more data with hyperspectral sensing. Thermal sensors getting much more miniaturized and low cost. For example, you can buy a $400 FLIR thermal infrared camera with RGB and radiometric capabilities there that can take images with with your smartphone. We of course have 2D and 3D LiDAR technologies that are becoming a little bit affordable, still between $10,000 to $30,000 there. And of course, there's always something new, and this is the combination of multispectral and thermal. A company in Seattle develops this, and we use this on a drone platform to capture both multispectral thermal imagery. But then again, as I said, just drone is just one capability to our platform to capture the images. We have seen a lot of developments in the low orbiting satellite domain, where, for example, Planet Labs and several other entities there, we have data up to 0.8 meter resolution, and frequency of every other day or something of that kind is becoming available, right? And so let's not ignore that aspect. And just to put things in perspective, we have about 7,000 or more satellites up in the air, and you can see from 2020 to 21, we have seen 28% more satellites going up, and this is just until June or July. And so right now it might be even more than that. So a lot of progression there. Again, same thing with weather sensing. A lot of, if you use weather app or something similar, you get this forecast, and all that is enabled by the satellites up in the air. And same thing again can be used with a little bit refinement to ag sector as well. Of course, the topography and all those things need to be factored in, and that's where we need to do what is called localized sensing. So for Washington agriculture, of course, we have what is called Mesonet. We have about 400 weather stations spread across the state 200 of our own and 200 that are private grower-owned stations, and all that data comes out, and growers can use that data. We are also seeing a lot of progression in what's called micronets. Some growers having 20 acre or between 20 and 100 acre, they are putting a lot of these low-cost weather stations. What you see here, and I have one that you can see here. So these are these weather stations capturing all the weather parameters that you want to, use for doing real-time decision making in agriculture to some extent. So with that perspective, I want to move on to talk about some use cases on how we use these sensors in my research group, and for some of the challenges that we have in Washington agriculture. I will start with something on the ground. This is the work that we have done to detect what is called leafroll disease in grapevines. And you can see if the vine is diseased, later stages, it shows the symptoms there, and there is no cure to this. You just have to remove the vine and stop the spread. And so early detection is key. And so there we don't have any sensors out there that we can put on the drone or on the utility vehicles. So we started with what is called hyperspectral sensor. This hyperspectral sensor has about 140 bands between 740 and 1780 nanometer there. And so we wanted to see how early we can detect this. And so all this work been done by Zhongwei, who graduated recently. And we found some optical bands that can detect this disease in earlier stages. And again, so this need to translate to other cultivars, see the combination of other diseases, and then go out to map this real time. And that needs some additional efforts there, but this is just a beginning there. Similar use of hyperspectral sensing to detect what is called early spring freeze related damage in the buds of blueberries. And again, as you know probably that the early spring is critical time for growers. Now even the summer is becoming a problem. We have a lot of heat stress issues, but early spring, as the blueberries or cherries or grapes, they're coming out of dormancy. We have 1 or 2 nights where there'll be low temperatures, and then the buds that are trying to become flowers and then the fruit, they will have damage, and then there is no flower and no fruit. So early detection is key there. So again, no sensors out there to detect this. So we started with hyperspectral and look at different growth stages and how early we can detect the damage if there is any. And again, that work is being published out there. So if you're interested, you can look at that. We have some optical bands that we have identified to detect this damage at earlier stages, again in non-contact way to some extent. This is moving to the air, like airborne sensing with drones. Again, low-hanging sensing with RGB and multispectral, 5-band multispectral imager. What we wanted to do is detect apple powdery mildew in the real settings, so that growers can use manual labor efficiently to prune the infected branches, or instead of spraying all the block, do surgical spraying, right? So, and again, apple powdery mildew is a big issue for apple growers. And so we wanted to see how the low-hanging, low-cost imaging can help there. So again, what you can see here is we have the RGB imaging, and then also the multispectral imagery-based indices. Here, what you are saying is normalized difference species index, red agent red, then green, and then blue. In this case, blue band was a little bit more efficient in detecting this infestation. You can see the healthy leaves and the infected leaves, again, in real orchard settings, that we could detect the powdery mildew. From there on, what we did is we went on to do what is called heat map or prescription map, so that grower can allocate the resources in a better way to manage this to some extent. Moving on, this particular use case, we use drone-based multispectral and thermal imagery and weather station data to do better energy balance. And the energy balance model was already out there to estimate what is called crop ET at a regional scale, 30 meter per pixel resolution with satellite data. So our efforts were to take this model and refine it to estimate ET at high resolution. for range of crops. What you are seeing here is the crop water use estimated by this energy balance model at about 7 centimeter per pixel using the drone imagery data and weather data that is there. And you can compare that with the granularity of the Landsat that you can see here. We cannot even see the rows and vines, but here you can see which areas of the block doing better and worse, and then change your frequency of irrigation or scenarios related to irrigation. And same thing then we applied for apple. Again, in apple scenario is a little bit complicated because growers not only irrigate, but also use what is called evaporative cooling systems to mitigate the heat stress. And so there's a lot of water that is going in. And so we wanted to see, can we see how the trees are using that water and identify the zones and such, so growers can again refine the irrigation scheduling and such. So again, that's most of it is published already. So I'll skip that. We looked also at, can we again use the thermal imagery and multispectral to understand the crop water stress and relate that to the stomatal conductance, the standard method of that, and understanding water stress in grape points. Another scenario, again, 3D LiDAR that you can see on the ground vehicle. What we did is the growers want to better manage the canopies. And so we threw this 3D LiDAR approach to do canopy mapping. And it's a lot of point cloud data that we analyze. And we realized that it's not, sorry, I had to go back a little bit. Okay. Not a lot of growers can do on their own, because collecting data is one thing, but analysis or analytics is different. And so we could do canopy mapping with 3D LiDAR. Of course, we did, but then it's too much data for a grower to handle. So we wanted to move to something simple, and then that's where we just use a drone-based RGB imager and do the double grid mission, where you are flying in one direction and then in the opposite direction, and then try to have different angles of this sensor to reconstruct the canopies and create what is called prescription maps that you are seeing here. And such maps, then again, growers can use like tree row volume, leaf fall area, or canopy volume to better manage the canopies, and also apply the chemicals at different rates if they have to. Again, something similar, simply just using multispectral sensor. Not complicating the issue, just look at the top view and create this what is called canopy area ratio, and see which areas of the vine are doing the vine block are doing better and which are not, and then grower again can use this for better canopy management throughout the season. A little bit going back to the IoT and some of the infield sensing, we have two projects now from NSF and USDA where we are developing what is called crop physiology sensing system. And the system, you can see the implementation here. These sensing nodes, each sensing node, what it has is a thermal infrared and RGB imager. The data is collected every 5 minutes on a Raspberry Pi, being analyzed real time, and then using OpenCV and Python scripts there. And in this case, one of the projects we are estimating what is called fruit surface temperature, an indicator of heat stress in apples in the summer, and then we can actuate, the evaporative cooling system to save the water energy and avoid the heat stress there. The similar concept can again be applied for, you probably know in summertime we get rain, and the maturing cherry fruit absorbs the water and cause splitting, so we cannot really harvest and sell that for fresh market. So knowing the wetness through the thermal imaging, and then using the ways to mitigate that, removing the water with the manned helicopters, that's what growers use, or orchard sprayers just running the air blast. So those scenarios, and we have recently funded with, again, from NSF to do something similar to understand the bud damage or bud temperature, and activating the mitigation measures for the frost mitigation in some of the sweet cherry and blueberry crops. So this is again actual implementation of the system that we have developed. What you see here is thermal RGB imager here, the all-in-one weather station up here. We also have temperature and humidity probe down here, and then all that data is being analyzed by the control box here, and then we are doing real-time actuation of the evaporative cooling. Again, we're using the modified foggers to save the water and all that. And and it's already being implemented in commercial orchard. I have the video. I'll skip that because I think we will run out of time. And again, something similar as we were doing this project and doing extension outreach, which is very important for some of the growers to use this technology. As we were doing that, growers said, okay, your technology will come in handy after a few years, but for now we need to have something that we know the fruit surface temperature and such. And so what we did is, again, this is a consumer grade thermal RGB imager that you can connect to your smartphone, Android or iOS. And we just developed an app that analyzes that image and give the actual fruit surface temperature and such. And we also, because we have the smartphone and GPS a receiver there, we are pulling the nearest weather station and use the energy balance model to estimate fruit surface temperature. So there are two ways growers will know how the heat stress is there in that block and then actuate the evaporative cooling as of now. So yeah. And again, we validated that for different cultivars that are there in the state of Washington that are kind of key, that are like kind of susceptible to heat stress. And yeah, next one, I think I talked about this a little bit. What we are doing here is frost mitigation, again, using a lot of in-field sensing nodes. You see here the wind machine, that is what is used to invert the air and avoid the frost. Growers also run the sprinklers or the burners on the side to increase the air temperature, and the wind machine is kind of inverting that air. So what we are trying to do, because Washington has different topographies, we have the weather stations outside with our ag weather network. We have in-field sensing now. We are doing this, and we are using a drone-based payload to map the inversion profiles, and then tying that everything together as a decision support to activate or mitigate to run these mitigation techniques there. Okay, let's wind down. Another aspect that we are doing here, a little bit on the sensing side again, is trying to see, can we use volatile sensing as a tool to identify stress in the plants. And we know for sure that for biotic or abiotic stress, plants do release volatiles, and there are a range of tools that are available, right? And you probably have seen all this. In some capacity, we have GCMS and the electronic nose type sensing devices. Of course, each of those are kind of have their own challenges and things like that. Recently, and you probably have seen these ion mobile spectrometers on the airports as you're going through security. If there is some suspicion, they will swab your bag and run this sample through the ion mobile spectrometer and get real-time alert that your bag is good or something is there. So same technology we are trying to use for detecting the plant stress-related volatiles. And some of the use cases that we have been trying is, one is again sweet cherries that we are number one in US for sweet cherry production, but the growers are really struggling with managing what is called little cherry disease. It is again caused by little cherry virus 1 or 2 or Western phytoplasma. So a range of cultivars that are susceptible to this. What the virus does is, you cannot see the symptoms until you see the fruits later in the stage, where those are little cherries, not as mature and develop as the normal ones would be. So there is no detection mechanism to this, and really you have to wait towards the end of the season and remove the trees again because they're infected. And so we are trying to apply this FAIMS field asymmetric ion mobile spectrometer and looking at the volatile profiles. And so far we have been, we have collected data for all the growth stages. And again, this is first year of this project, where we can detect the peaks related to LCD at the harvest stage, and we want to go back to different growth stages and see how back we can go to some extent. Similarly, again, this is related to potatoes. We have what is called Pythium leak and soft rot in potatoes when they are stored, because in US we store the potatoes with, harvest them without cleaning. You dump in a football soccer field like facility that is enclosed, and reduce the temperature and increase the humidity to some extent. And there we see a lot of the soft water. We throw several tons of 100 tons of potato on a given day, because this is soft water is an issue there. So we are trying to again use this ion mobile spectrometer and see, can we detect the soft rot, and we have some success there. We have published this work heavily. So if you're interested in this, please have a look at it. So closing up again, for me, because I work in the field, and precision agriculture has to be tying the monitoring with management, and there are a range of technologies that are emerging to manage scenarios in crop systems, and you will see a lot of that propagation in coming years. The future, of course, you're seeing we are switching ourselves from conventional way to doing things to smart ways, and same thing is going to happen for agriculture. The issue is, digital, as we try to digitize things, agriculture, the workforce, everything need to factor in. We are least digitized industry, and as we try to push some solutions and some technologies here, the workforce training and education, grower education is very important piece there. So just want to throw it out there. With that, I just want to acknowledge all the hardworking people in my lab and my collaborators. Really, I'm just representing them here. And yeah, I will stop here. Thanks again for the opportunity. Yeah.
Thank you, Dr. Khot, for a wonderful presentation. It's exciting to see the different applications in the field. So I'll ask one question because we are getting close to our time. Have you tried any types of sensors below ground in the field?
Yeah, no, we have not. So I try to stay above ground as much as I could with optical sensors and such. Of course, we have been using the soil moisture, soil water, soil nutrient type sensors, but I'm just a user of those sensors to some extent. We have not explored or developed new type of sensors to there in that capacity. Yeah.
Thank you. So I encourage everyone to ask all the questions you have in the Discord channel so we can keep this conversation moving. Thank you again for a